Okay, here's your chapter on radiation effects and safety. So you have a bunch of objectives. It's really important that you're able to describe and list and explain the different items within this chapter. So lots of them, lots of key terms. You need to be able to define these key terms. So looking at radiation units and measurements, there's two different systems. There's the traditional and the SI units. So when we're talking about the traditional units, these are going away. So your national exam now only uses the SI units. So we're still going to talk about the traditional units because you still need to know. A lot of texts and textbooks still use the traditional units. They're getting better about using the SI units. But when we talk about traditional units, we're talking about the Rankine. It's symbolized by the capital R, and it's a measurement of intensity in air. So it produces 2.08 times 10 to the ninth ion pairs in 1 cubic centimeter of dry air. So the important part is that you know that it's the Rankine, and it's the capital letter R, and it's a measurement of intensity in air, okay? So if we look at the SI unit, the SI unit of the Rankine is coulombs per kilogram, and it's symbolized by the C/kg. And it's the quantity of electrical charge in coulombs produced by exposure of 1 kilogram of dry air. So similar, okay? So air is what we're talking about. So it's the measurement in air, okay? So 1 Rankine equals 2.58 times 10 to the fourth kilogram coulombs per kilogram. So it's not a useful dose measurement is the biggest thing. So if we're looking at dose, we're not using this. We're just looking at the measurement of intensity in the air, then that's what we're talking about, either the Rankine or the coulombs per kilogram. So if we go into radiation absorbed dose, which we call the RAD, this is the traditional unit. The SI unit is the gray. So 1 Rankine of exposure will result in about 1 rad of absorbed dose in muscle tissue. So the Rankine is in air and the rad is actually within the body. So what was absorbed by the body. So the gray, so 1 gray equals 100 rad. So we usually have centigrade. So 1 centigrade equals 1 rad. Okay, so looking at the units in a chart here, so we have our exposure units, which is the coulombs per kilogram, and in the traditional, it's the Rankine, and it's the radiation intensity in air, where our dose units in the SI is the gray, and 1 gray equals 100 rad. So in the traditional units, the radiation absorbed dose, rad, is 100 ergs per gram of tissue. So just remember the gray and the rad are dose in tissue, where dose equivalence is the sieverts. So this is another one. It's the sievert is the SI unit, and it's the Rankine equivalent man. So it's the REM. So when you look at your radiation dose monitors, it's going to be, your report will be in REM. So that is our occupational dose. So the company has not converted yet to sieverts, but so it's important that you know the REM is occupational dose. So it's called dose equivalent units, and in the SI units measured in sieverts. So the sievert is a gray times the weighting factor, and 1 sievert equals 100 rem. So radiation weighting factors. The biological effect of radiation exposure varies according to the type of radiation involved. So occupational dose may be a combination of different radiations. So for example, nuclear power plant workers and nuclear medicine techs. So the weighting factors is a process of measuring occupational dose. So there's different types of radiation have different weighting factors. So some are more potent than others. The absorbed dose is the dose equivalent is the absorbed dose of radiation is multiplied by the weighting factors. So the sievert, which is the SI unit, or the radiation equivalent man, which is the REM, which is traditional units. So there's that equation again. 1 sievert equals 100 rem for the equivalent. So when we look at the weighting factors, so X-rays have a weighting factor of 1. So it's 1-to-1. So if we look at protons and charged pions, we look at 2. If we look at alpha particles, which are really, really damaging, it has a weighting factor of 20. So just to give you an idea, it's important that you know that X-rays have a weighting factor of 1. Okay? So looking at Rankine and coulombs per kilogram used to measure the presence of radiation in air, the rad or the gray used to measure radiation dose, and the sievert or the REM is used to measure occupational dose using weighting factors. So biological effects of radiation exposure. So the laws of Bergoni and Troubrdet states that cell sensitivity to radiation exposure depends on 4 characteristics of the cell. So age of the person, differentiation, metabolic rate, and mitotic rate. So if we look at the age, so younger cells are more sensitive than older ones. So babies, naturally, their cells are really young and they're dividing quickly. So differentiation is non-specialized cells are more sensitive than highly complex ones. Metabolic rate, cells that have use energy rapidly are more sensitive than those that with a slower metabolism. So with babies, they're growing really fast. So the young cells are sensitive along with the rapidly dividing cells. And the mitotic rate, cells that divide and multiply rapidly are more sensitive than those that replicate slowly. Okay, short-term deterministic. So it's also non-stochastic somatic effects. So you'll see it listed either way. Those that affect the body of irradiated individuals directly. So observed within 3 months of exposure, associated with high radiation doses, so above 50 centigrade, and further characterized according to the body systems affected. So it'll affect the central nervous system, the GI tract, blood effects, occurs only after a certain amount of exposure has been received, and the severity is dose dependent, so depending on the amount of radiation that the person has been exposed to. All right, so this is seen quickly. So if we look at the biological effects of radiation exposure with deterministic radiation effects are short-term somatic effects associated with high dose exposures. They are predictable and their severity is dose dependent. So we know what's going to happen with certain amounts of radiation in the short term and in long term. And they can fluctuate depending on how much the patient did receive or you received. All right, so long-term somatic effects, sometimes referred to as latent effects, may not be apparent for as much as 30 years. So sometimes manifests itself in 5 to 30, but the greater percentage is 10 to 15 years before you see any effects of the radiation exposures. So stochastic effects, long-term, 5 to 30 years until manifested. Most likely happens from low dose exposures, but are still random in nature. So no threshold amount of exposure must be received for this to occur, and greater likelihood when dose is increased, but no correlation between dosage and severity. So it may occur as a result of repeated small doses, such as those in radiography. So if you have a chest x-ray or CT done every day or every week over a long period of time, that's what we're talking about. So latent effects of low dose ionizing radiation include cataragenesis. So we can form cataracts. So it's clouding of the lens of the eye. So exposure to radiation, your eyes are very sensitive and you can get cataracts. Carcinogenesis is increased risk of malignant disease, so the skin, thyroid, breast, and leukemia. And there can be lifespan shortening. So radiologists have been found to have a shorter lifespan than other types of doctors way back when. Today's world, overall very safe. So genetic effects, we look at damage to the reproductive cells of the irradiated person, mutations to the genes when ovaries and testes are irradiated, and damage observed in children or in grandchildren. So genes that are expressed are said to be dominant, and those that are not expressed are recessive. So mutated genes are usually recessive. So if we look here, genetic effects occur as a result of damage to reproductive cells irradiated, and we see them in our children, grandchildren. So radiation safety. So we look at personnel safety, personal monitoring, effective dose limits, patient protection, and gonadal shielding. So personnel safety. So radiographers are classified as occupationally exposed, so prohibited from activities that result in direct exposure to the primary X-ray beam. So you should never be exposed to the primary beam. So you will be exposed to radiation, but not the primary beam. And the three methods, principal methods of protection, this is very, very important that you know this, is time, distance, and shielding. Those are the three cardinal rules. Is you want to minimize your time, you want to maximize your distance from the source or the scatter, and you want to always be shielding yourself. So this is a Landauer badge right here, and this is just the same as your badge that we use that clips on. Is the little jump drive. So it's the same difference. This one we have to mail in and have it read, where yours we can just pop it in the computer, which is great. So everybody working in radiology should have one of these badges on at all times as part of your uniform, and you're not allowed to work without one. And this is a ring. It's a radiation detection for nuclear medicine technologists when they are drawing up radioisotopes, that they wear these dosimeters on their fingers so that they can see how much radiation dose that they've received. So dosimeters are devices used to monitor personal radiation exposure, worn at the collar level facing out, and there's a lot of different types of badges that we'll get into later. Effective dose limits. So we use this philosophy of ALARA. So we go as low as reasonably achievable. So 50 millisieverts per year is the effective dose limit for occupational exposed individuals. So a cumulative lifetime dose is equal to 1 rem or 10 millisieverts times the worker's age. So you just say, okay, how much have you received and how old are you? So your effective dose limit also exists for specific organs within the body. So radiation, patient protection, so principles to minimize patient dose. What you want to do to protect your patients, you want to double check your requisition and the patient ID so that the right patient receives the right examination. Avoid repeats. Establish and follow routines and avoid careless errors. Unsatisfactory images must be repeated. So be careful that you're doing it right the first time. Collimate. Use the smallest radiation field possible for the anatomy of interest. Use the highest kVp allowed for the part and image quality. It allows you to use the lowest MAS to minimize the dose to the patient. And we'll get further into that when we get to physics. Use at least 40-inch SID. So it limits patient exposure from the tube housing leaking and the collimator scattering. So you are not allowed, according to Title 17, which is state law, to take an exposure shorter than 40 inches. So 40 inches is the minimum distance. You are not allowed to go below that because of the dose to the patient. You want to use as fast image receptor as you can get. So in film screen or in CR and DR, they have different speeds. The faster the IR is, the less detail you're going to get. So you want to find something in the middle. But the fastest IR you have reduces patient dose. So there's a compromise somewhere in there. You always want to provide shielding. So to the gonads, the eyes, the breast, the thyroid, or wherever the patient is asking. So gonadal shielding defined as lead shields of at least 0.5 millimeters of lead to prevent unnecessary radiation to the productive organs. It limits the genetic effects of radiation and required when the patient is of reproductive age or younger. And your site will tell you we do it on everyone below 60. So you just have to find out what the age is. And if a patient asks for it, and they're 90, shield them, why not? So requires when a patient So when the patient is reproductive age or younger, gonads are within the primary radiation field, and the shield will not interfere with the exam. So this is generally applies to most patients younger than 55. So 55 is the general, but some places say 60, 70, whatever it is. And so you can see here on a male, we will shield below the pubic symphysis. On a female, we'll shield above the pubic symphysis if we're taking an x-ray of someone of reproductive age. Now, getting the shield right on a female is really hard. And if you're off on your placing your shield, these are called shadow shields. And if you're off placing this little shadow shield, then you're going to have to repeat the image. So a lot of us do not use these shields because you'll have to repeat the image, which is double the dose. So, I'd rather radiate the ovaries once than, twice. So anyway. Radiation in pregnancy. So greater risk to fetus for radiation exposure in the first trimester. We do everything we can not to radiate that baby in the first trimester. The cells are growing really, really fast, and you hit the DNA of one of those cells and it reproduces incorrectly, you've got a problem. So occupationally exposed pregnant workers have a 50 millisieverts effective dose limit for the whole body over the 9 months of pregnancy. So what we do is we give you a normal radiation badge and we give you a secondary badge, and you're going to wear lead the whole time you're around radiation. You're going to have that radiation badge on the inside of the lead because we want to see what the baby is receiving. And overall, very, very safe. I've had several pregnant students, which I don't recommend you get pregnant while you're in the program, because I make you wear lead all day, every day, and wear an additional radiation badge. Not to mention you're on your feet for 8 to 10 hours a day, and it's exhausting. So I don't recommend you get pregnant, but if by chance you do, then you have to declare it in writing according to the state of California. So you declare your pregnancy in writing, and we go ahead and order you a second radiation badge to monitor the baby, and you are to wear lead while you're in clinic. All right. And the radiation dose that comes back has been 0 for all of my pregnant students. So these signs are on the door, on the wall, or wherever. So if you're pregnant or you think you're pregnant, tell the technologist before taking the x-ray. You do not want to x-ray someone who is in their first trimester. So regulations require that female patients of childbearing age be advised of the potential radiation hazards before the exam. Signs in the department advise women to tell the radiographer before the exam if they might be pregnant. So a lot of times there's going to be documents that you're going to have the patient sign stating that they are not pregnant and signing with their last normal period. So, and if they won't sign that, then you need to send them for a pregnancy test. That's very common in the workplace because you do not want to radiate a pregnant patient. All right, that's your lecture. Make sure you read the book also.